Welcome friends. I am Professor Mohammad Tariq, Department of Economics, AMU Aligarh. In the last lecture, we talked about the path when the portfolio is being made between two assets. The asset we term as asset 1 and asset 2. Now, suppose if there are n assets, then in that situation, what will be the feasible set? So, today we will be talking about the feasible set. If more than two assets are there, so suppose there are n assets and this feasible set will be explaining this with the help of a diagram, in R sigma plane. Means on one axis we'll be taking mean rate of return and another axis will be taking a standard deviation of return on assets, which reflects the risk factor, and this reflects the average return factor. So this if the investment is being made into n assets with weights wi means w1 w2 up to wn, such that sigma wi this is equal to 1. So let us try to understand this investment in case of if there are three assets 1, 2 and 3, then the boundaries created by that asset, the path created by that asset, that will be a solid region. That will be a solid region. The feasible set will be a solid two-dimensional region. In the last class, we had already talked about that if the assets are correlated, like 1 and 2 are correlated, return on that asset is correlated, or 1 and 3 is correlated, or 2 and 3 is correlated, the path will not be a straight line, rather the path will be a curved one inside a triangle, and that will be convex to the mean rate of return axis. So similarly, if this is R bar, this is sigma, the different assets are there being denoted by different combinations of mean rate of return and the standard deviation. This is asset 1, this is asset 2, this is asset 3. So there could be this path between 1 and 2, the another path will be 1 and 3, there could be a path between 2 and 3, and between 2 and 3 there is another asset, suppose 4, another path could be there 1 and 4. So what do you find? All these family of all these curves, all this make a solid region in two-dimensional graphs. In two-dimensional frame. If n assets are there, so the n assets could be if n assets are there, so these n assets could be denoted by this R bar sigma is there. Now this could be Many assets are there, so the path will be like this. Clear? So this is the case when we have this shaded line and no shorting is taking place, no selling is taking place, no shorting is taking place. But with shorting, what will happen if there is a shorting? In that situation, this will be covered by a shadow. This area will increase because some of the weight will be negative. So this area will increase, and with shorting, this will be covered by a shadow region. Clear? So this is your all about the feasible set. So all the feasible sets will be like this, and the investors will invest to the left of this curved line and up to this, not beyond this. Clear? So these are left means where the variability, the risk factor will be lower. So the consumer investor will try to invest in less risky assets. They try to invest in less risky assets. Clear? They try to invest in less risky assets. So this is called as a feasible set. Now, uh, within this feasible set, if we try to find out the efficient frontier, the efficient frontier within this feasible set, so efficient frontier can be obtained like this. We take two lines, one horizontal line, another vertical line. What is the significance of drawing this horizontal line in this feasible set? Within this feasible set, the horizontal line, suppose this is horizontal line, suppose if this is there, along horizontal line your rate of interest is fixed. Rate of return is, the average rate of return is fixed. R bar. So if at this fixed rate of return, if investor make an asset at this point, then at this point, and you make comparison between this point and this point, what is the difference? At this point the variability is higher, at this point the variability is lower, and at this point along this efficient frontier, at this point the variability is lowest. Beyond this point the investor will not go. This is a case of short selling, and the weights will become negative in that situation. So the investor would like to make investment on a point which is which provides the lowest standard deviation value or with lowest risk. So this type of investor with fixed average rate of return, investment done on asset with lowest possible sigma along efficient set. So the lowest possible sigma is at this point this is the lowest possible. For this, the fixed rate of return will be this much. So this point is known as, within this efficient set, or efficient within this feasible set, efficient along efficient feasible set. Within this efficient feasible set, the lowest point is this much, and this lowest point, this is called as minimum variance point. This is one way of looking at efficient frontier, when we have fixed this rate of return. In the similar fashion, we can also fix sigma, not the rate of return. We can also fix sigma, and in that situation, if sigma is being fixed, then investor would like to make investment. This is the point, minimum variance point. Let this MVP. So this is MVP, minimum variance point. So this, if this is your sigma f, now in this situation, the investor would like to invest at a point which yields him the highest amount of return. Here the rate of return will be low, here the rate of return will be low, and highest will be at this point. With this risk factor, with this sigma factor. Clear? So with this MVP, minimum variance point, over here MVP, and with given variance we have this one, the highest rate of return, because every rational investor, he prefers more money over less money, or more return over less return. So the higher return is being preferred. So what you can say, the efficient frontier will be combination where we will be combining both this, the result from by doing the horizontal line, or the result drawn from the vertical line. And efficient frontier will be this portion of the portion MVP above minimum variance point, above this. So this is your efficient frontier. So efficient frontier will be decided on the basis of this. Clear? So this is all about the concept of the feasible set and the efficient frontier. Now, what I told you, the decisions are being taken by the investor on the basis of mean rate of return, on the basis of sigma, and on the basis of this covariance. The variability term, the sigma term, this is an indicator of the risk factor. Here in this case, the risk is minimum, so the investors are being called as risk averter. The investors are called as risk averter. If in this situation the investor does not make investment at this point, rather at this point or some other point, so we will call such type of investors and risk lover. Here we find if more return is being preferred or more money is being preferred to the less money or less return, this is known as the axiom of non-satiety. Axiom of non-satiety. So these two, the risk efficient frontier is being determined by risk aversion as well as non-satiation. The basis of this risk aversion and non-satiation. Now this risk factor, this is the graphical analysis or some theoretical analysis you can say. This every investor tries to minimize this risk, and this we can do mathematically also, taking the help of mathematics we can do this. And here we'll be using the concept constraint of optimization. Mathematics constraint optimization, and here the optimization is nothing but it is related to minimization. Yeah. Here we will be using the concept of Lagrange multiplier. What is this? We had in the last lecture already derived that this if n assets are there with n assets with return R1, R2 bar, R3 bar and Rn bar with a standard deviation with SD denoted by sigma ij, variance covariance, and the weights denoted by Wi, means W1, W2, Wn, such that sigma Wi is equal to 1. So here the objective function is the minimization of sigma Wi, Wj, sigma ij, this half ij to 1, 2, and the half we have taken divided it by 2 just for the sake of reaching at some concrete conclusion. There is no, we should not give much significance to this number 1 by 2. And what are the constraints? The constraints here are sigma Wi Ri bar, I is equal to 1 to n, this is equal to R bar, and sigma Wi is equal to 1. So the two constants are there. So this minimization of objective function is being done with the help of the use of Lagrange multiplier. Two constants are there. We will be using two Lagrange multipliers. Let one be denoted by over here lambda and another be denoted over here by mu. So first we write down this equation in the implicit format, like sigma Wi Ri minus R bar is equal to 0 and sigma Wi minus 1 is equal to 0. This is implicit form of the equation. Now what this, we write down composite function. The composite function is phi, this is equal to 1 by 2 sigma Wi Wj sigma ij minus lambda sigma wi ri minus r bar minus mu sigma wi1 I minus 1 minus 1. So this is how we write down. Now we have to minimize this function. For this, what we have to do is the first order condition, FOC, first order condition for minimization. This needs to be differentiated with respect to every wi and wj. So sigma wi is equal to 0, phi wj this is equal to 0, delta phi upon delta lambda equal to 0, and delta phi upon delta mu equal to 0. Clear? In this process, if you differentiate it with respect to this, you get the two equations from here and n equations from here. So in total, we will have n plus 2 equations and n plus 2 unknowns. So this can be solved. This is a bit complicated one. So for the sake of simplicity, we'll be taking two assets only. And with the help of these two assets, we'll derive certain, we'll reach at certain result. And after reaching a certain definite result, again we will generalize the result. Like we have written here the general form of the equation. Now suppose if we confine to two assets 1 and 2. Clear? So the weights assigned will be the rate of return will be R1 dash R2 R1 bar R2 bar. Weight assigned will be W1 W2. Variance will be sigma 1 square and sigma 2 square, and covariance will be sigma 1 2 or sigma 2 1. The covariances are symmetric in nature, so they both will be equal. Sigma 1 2 will be equal to sigma 2 1. So rewriting this equation for two variables only, rewriting this equation for two assets only. This phi, this can be 1 by 2 sigma w1 w sigma w1 square sigma 1 square plus w1 w2 sigma 1 2 plus w2 w1 sigma 2 1 plus w2 sigma 2 square minus lambda w1 r1 plus w2 r2 minus r bar w1 r1 bar. So here it will be bar. Clear? Minus r bar minus mu into w1 plus w2 minus 1. Now here just take delta phi by delta w1. This is equal to 1 by 2 twice sigma 1 square w1 plus w2 sigma 1 2 plus w2 sigma 2 1 w2 this minus lambda r1 bar minus mu is equal to 0, delta phi upon one by 2 w1 sigma 1 2 plus W1 sigma 2 1 plus twice sigma 2 square into W2 square, sorry, W2 square minus lambda R2 bar minus mu is equal to 0. And the two additional equations that we will be getting in the form of delta phi upon delta lambda. This will give you, if you put this equal to 0, this will give you W1 R1 bar plus W2 R2 bar equal to R bar, and delta phi upon delta mu equal to 0. This will give you another W1 plus W2 is equal to 1. So we have four equations, 1, 2, 3 and 4. So four linear equations, 4 unknowns, W1, W2, lambda and mu. So we can solve it easily, solve and get a unique solution. We can solve it and get a unique solution for this. Clear? Now we'll go and rewrite this equation. This equation will rewrite in the general form. So how this sigma 1 2 is equal to sigma 2 1, so the both are equal. Sigma 2 1 and sigma 1 2 is equal. So this equation you can write down this plus this. So this will be 2W2 sigma 1 2 or sigma 2 1. This is 2W1 sigma 1 2. So we write down 2W2 by combining these two equations, as sigma 1 2 is equal to sigma 2 1. This way we have already mentioned. This is by symmetry. The covariances are equal. So what we can write down, this 2 will get cancelled out. Sigma 1 squared W1, sigma 1 squared W1 plus W2 sigma 1 2. So this can be written as sigma 1 squared W1. This can be written as sigma 1 squared W1 plus sigma 1 2 W2. Sigma 1 2 W2 minus lambda R1 bar minus mu is equal to 0, and this is sigma 2 squared W2 plus sigma 2 1 W1 minus lambda R2 bar minus mu is equal to 0. The generalized form of this equation, this can be written as, when we go for n assets, the generalized form for n assets, we can go and write it down like this: sigma ij wj j is equal to 1 to n minus lambda ri bar minus mu is equal to 0, where for I is equal to 1 2 3 up to n, and sigma wi ri bar I is equal to 1 to n, this is equal to 0, and sigma wi is equal to 1 to, and this is equal to 1. So we will have n equation from here, 1 to n, and one equation and one equation, two equation over here. So in total we have here n plus 2 equations with n plus 2 unknowns. Clear? So this theorem, theorem through which we are trying to minimize the variance portfolio. So this result through which we try to minimize the variance of portfolio. This was given by Markowitz. So this is known as Markowitz theorem. And it is on the basis of this result of Markowitz theorem that we shall be in a position to talk about two-fund theorem and one-fund theorem. So in the next class we will discuss about the two-fund theorem as well as the one-fund theorem, and there we will be using this concept, this result of minimization of variance of portfolio. Minimization of variance of portfolio will be talking about the two-fund theorem and three-firm theorem. Clear? So n plus 2 equation, n plus 1 unknowns. So here also you can get unique solutions.